This is a moon exploration vehicle. It is an achievement of the science and technology of many men working together, the result of man's urge to explore the unknown. This manned orbital laboratory, or one very much like it, will carry 3 men far out into space, and, most important, this reentry section will bring them back. Where do we find this carrier of future adventurers? Above the Earth? On the way to the moon? No. Actually, our cameras find it today at Farmingdale, Long Island, New York, in Republic's vast new laboratories, designed and ready now to explore space. We ask you to be part of a behind-the-scenes story here at the Paul Moore Research and Development Center, a combination of facilities under one roof like no other in the world. Republic is one of the organizations which may be making the future headlines of American space accomplishment. How did this come to be? This was a man with a dream. A man who could dream of tomorrow's reality, who was not limited by time. His dreaming reached far and high. Years ago, Paul Moore, in his belief that our country must be well protected, foresaw the necessity of a climate in which men might develop creative and long-range thinking to meet the challenge of the aerospace age. Republic, listening with a thoughtful ear to this voice from the past, has created such a workable climate in which a group of scientists may together discover and harness the knowledge needed to launch the greatest and most daring voyage of exploration ever contemplated. This is a space vehicle of the Apollo type. You may call it what you will. Its destination, Earth. Its trajectory around the moon. The distance about 500,000 miles round trip. Time of departure, yet to be determined. Down these halls work other practical dreamers, the designers and planners whose thinking is supported by the men in the laboratories. Ideas begin in the minds of people. It is people who design and build the devices, the hardware, the vehicles to accomplish the planned missions. It is people who count. Here at Republic, the people are ready. They are primarily specialists in such fields as life sciences, medicine, solid-state physics, thermodynamics and aerodynamics, psychology, physiology, nuclear physics, radiology, metallography, astronomy and chemical engineering, electronics, and guidance. But they need more than conference tables, slide rules, and ideas if this nation is to discover how space can best serve man. In the Paul Moore Research and Development Center, the tools they need exist today in a combination that cannot be found in any other place in this country. At Republic, right now, there exists the total research and development capability to design and build the vehicles that will take man to the moon and beyond and return him home safely from his journey. And the Paul Moore Center is in truth a total research and development capability. Reentry, fluid systems, radiation, guidance and control, electronics, space environment and life sciences, materials development, all integrated laboratories oriented toward a common goal. And the countdown has already begun in every one of Republic's new labs to meet the challenge of the cosmos, to overcome the hazards of space flight, to control the maelstrom of the G-force, to provide a shield against cosmic rays, to demonstrate to the peoples of the world that America can assume leadership in the age of space if she will. She may successfully leapfrog present thinking to enter an entirely new era of space development. So let's explore with our camera the challenges one by one, the steps being taken to overcome them. I'll ask our cameraman to show you what you might see if you were here with us in Farmingdale.
I'll try to keep up, but if I don't understand what you're talking about, can I ask a few questions?
By all means. This design symbolizes the work of the reentry simulation laboratory. Reentry of the vehicle through the atmosphere and return to base is one of the most critical phases in space travel. This hypervelocity shock tunnel, 96 feet long, subjects the precise vehicle configuration to reentry conditions. As you are aware, the men in our lunar vehicle will return from their mission at a speed of 25,000 miles per hour. Such speed produces enormous temperature problems, capable of burning up both vehicle and occupants. Right here in this chamber, for at least a portion of a second, we are able to measure the heat transfer to the vehicle at speeds up to Mach 20 and temperatures of 18,000 degrees Fahrenheit. The air supply is heated and compressed by a strong moving shock wave. And then, after it is heated and compressed, it is allowed to expand through this nozzle. This is Dr. Robert Perry, Ph.D., Cornell University, director of this laboratory. Dr. Perry has specialized in strong shock waves since 1947.
You have just seen an important part of the reentry laboratory. Another vital component is the arc jet, which is really a very high temperature blowtorch. With the arc jet, we can determine the effects of aerodynamic heating at temperatures up to about 27,000 degrees to study their effects on the ablation materials of the reentry vehicle's nose cone.
What's ablation?
That's the melting and vaporization of nose cone material during reentry into the atmosphere at hypersonic speeds.
Can we see this blowtorch in operation?
Certainly. Mr. Champney, the engineer in charge of our arc jet operations, is all prepared for a demonstration right now.
In here, then, you can solve all the problems of reentry.
Yes, but there's one other problem that must be investigated. What happens to Apollo in a meteorite shower? Here's where we can find out. Our ballistic range, which is now under construction. This is no ordinary ballistic range, though. It's a high-velocity hydrogen gun with which we can produce free flight of a small projectile through simulated high-altitude conditions to test meteorite showers and impacts.
How do you test for impact?
Well, we can observe the results photographically and, of course, see the effect of impact on the model itself after the test. You will see a smaller 41 millimeter shock tube in the background. Both of these devices were built in our own shop.
Is this what you would call a typical space reentry laboratory?
Other laboratories may have some of these tools, but I don't believe that any other laboratory in this field has such advanced devices of all these types under one roof. Since no single test facility has yet been developed which can reproduce all of these effects, and all of them are necessary if we're going to put Apollo up there and bring it back safely.
Our thanks to you, Dr. Perry, for a most unusual tour. Republic's reentry laboratory, putting to work the tools of the mind to speed Apollo from drawing board to launching pad, from Earth to Moon and back. The problem here, as Apollo re-enters the atmosphere at 25,000 miles per hour, not only the nose cone, but also the movable surfaces and control systems of the vehicle will be severely heated. Working on the solution to ensure that control systems will function reliably regardless of heat is the Fluid Systems Laboratory, under the supervision of William Mayhew, a graduate of the College of the City of New York, 17 years in aeronautical engineering.
Consists of 5 test cells and supporting equipment facilities, all of which will be used to make sure that Apollo's fluid power system will perform reliably.
How does all this equipment work? What does it do?
These hydraulic and pneumatic power packages furnish high-pressure, high-temperature fluid to test stands in adjacent cells as well as to other areas throughout the laboratory. This is a multi-chambered oven in which complete subsystems can be operated at temperatures up to 1900 degrees Fahrenheit and at pressures up to 5,000 pounds per square inch. Here we simulate the performance of control surfaces. Different temperature levels can be maintained in each of the three chambers independently. For instance, right now we're preparing to test a 1,000 degree Fahrenheit hydraulic system. However, we're not restricted solely to developing hydraulic systems. An important part of our operation is the development and evaluation of the pneumatic systems which may be required on vehicles similar to Apollo. Gaseous systems will have certain advantages over liquid-type systems in some applications. With the equipment we have right here, we can readily perform necessary developments in both areas.
Mr. Mayo, you mentioned 5 test cells.
Yes, that's right. 2 additional cells, not requiring the stands or the power packages, contain portable ovens which can be shifted to other parts of the laboratory for additional testing. For example, one of our problems is the examination of fluid systems in a combined high-temperature and nuclear radiation environment. The ability of components, such as an actuator, to withstand nuclear radiation effects will be investigated in the radiation laboratory.
Thank you, Mr. Mayo. Problems of solutions of reentry. Fluids, the bloodstream of Apollo. Now, still another problem to be solved as the countdown continues. Radiation, an ever-present threat to our space vehicle and to its crew. Meeting the challenge, the Nuclear Radiation Laboratory. It is under the supervision of Walter Barron, B.S. Cooper Union, M.S. Brooklyn Polytech, basic nuclear training at Oak Ridge School of Reactor Technology, 18 years of experience in engineering and in physics.
This entire field is challenging, but that's what makes it interesting. Our investigations are concerned with 3 basic areas of nuclear radiation: as a measuring technique, as an environment, and as a power source. This hot cell enables us to use high-intensity radiation sources in performing our experiments.
Hot cell? You're inside a hot cell now?
Yes, and here's the hot part. Right there, under 17 feet of distilled water, is a 40,000 Curie cobalt-60 source. It's a gamma source of high intensity, one of the largest in the country. I don't know whether your camera can pick it up, but it's an attractive sight. It has a blue glow caused by Cherenkov radiation.
Mr. Mayhew just mentioned to us that you've got one of his actuators here.
Yes, here it is. We're going to be simulating the effects of temperature and nuclear radiation environments on an Apollo hydraulic system. This is a presently unloaded source rack into which it fits. We're also going to do a wide range of material effects studies starting now. We're doing preliminary radiation work on spacecraft materials such as plastics, transparent materials, solar collectors, and so forth. In the measuring area, we have a proposal we're working on using different types of portable radiation measuring devices. And in the field of power sources, we have developed some promising new concepts. Also, we've made provisions to install a particle accelerator to expand our experimental capabilities. The roof of the laboratory has been designed with removable sections for this purpose. It's in our future plans.
Mr. Barron, there are other radiation labs around the country. What makes your particular setup so special?
What makes it special is the combination of all the things you've seen on your tour and our ability at Republic to use them together. In our current programs, we are working in conjunction with a number of the other laboratories in this building. And if we weren't all under the same roof in the same area, this would be next to impossible.
Thanks, Mr. Barron.
You're welcome.
The Nuclear Radiation Laboratory, ordinary by itself in our time, but unique in being part of an integrated combination designed to shield and protect Apollo's crew and components, ensure its readiness for departure, but even more important, ensure that it comes home again. The Republic countdown continues. The problem to keep Apollo on its course, literally as well as figuratively. This is the function of guidance and control. Guidance and control is one of the support-type laboratories which enhance Republic's capabilities as complete systems managers. The director, John G. Urbanick, graduate of Rochester and Adelphi College, has a background of naval engineering and gunfire control, precision tracking, and stabilized navigational equipment. This is Mr. Urbanick.
This is a general view of the computer and control systems development section in which we are working on the applications of computers for space vehicles.
And here is the project manager for Apollo, Robert Rickles, specialist, aeronautical engineer, associate fellow, Institute of Aeronautical Sciences, member of the American Rocket Society, with 11 years of experience in reentry problems.
This is our gyro room, with the window here oriented to the North Star. This slab going down 10 feet is made of solid concrete. It makes possible the mounting of angular and linear devices such as this theodolite to make very accurate measurements.
What's that machine in the corner?
A very precise linear measuring device. This work area is intended for the development of exotic inertial devices, star trackers, and moon trackers. And in the next room, we evaluate optical infrared detection and reconnaissance systems.
What's that table in the center?
This is a lens bench with an autocollimator.
How's that again?
An autocollimator. This provides us with an artificial man-made star right here in the lab. And to check these various devices, we have this infrared spectrophotometer. And over here, Mr. Halpern is working on a prototype of a laser.
In this lab, too, we are doing considerable research in solid-state physics, the development of sub-miniature electronic components through our studies on thin film technology. And there is one other important function of this support lab which I think is worth mentioning. We have right here the facilities for evaluating equipment and components supplied by subcontractors in terms of the overall system for which they were designed, such as our lunar reconnaissance vehicle.
This guidance and control laboratory is another unique combination of many tools under one roof, another of the 7 integrated and interrelated facilities to measure acceleration, to guide our spacemen where they want to go, to keep them on course, trace their trajectory, and bring them back to Earth. Time is moving on. One big problem to devise a program for communicating with Apollo during re-entry while the vehicle itself is enveloped in heavily ionized gas layers. Conducting specific research in these areas, the Electronics Laboratory, under the supervision of Dr. Hans Wolf, Technical University of Berlin, inventor, and for the past 38 years associated with electronic research and development projects both in Germany and in the United States. What sort of research are you doing here, Dr. Wolf?
Specifically, the Electronics Laboratory will investigate problems associated with interspace communication systems and advanced instrument techniques. Our program is directed toward new means and concepts which we will work on in conjunction with our other laboratories. One important problem on which we are working is the development of a technique for communicating with Apollo during the re-entry phase, when it is enveloped by a heavily ionized layer of gas. We haven't solved it yet, but with the equipment we have here, we are making very good progress. We do this indoors, taking precautions, making certain that the space be free of echoes. It is a place where with great convenience we can make measurements on antennas. Also, very important for the Apollo program, we can make determinations of the vehicle radar cross-section for observation by radar. We call this skin tracking. If this were a weapons system, of course we would be trying very hard to do the opposite, to make it as difficult to see as possible.
Could you give us a demonstration of this chamber, Dr. Wolf?
Yes, by all means. You will notice that the turntable in the chamber carries the model of the Apollo configuration. You notice the rather unusual shape of the chamber's walls, which give us almost echo-free microwave measurement capabilities.
Do you have any other photogenic devices, Dr. Wolf?
Not so photogenic, but very important. The standards room. It contains a large number of electrical precision instruments.
And their purpose?
The purpose here is to have highly reliable and accurate reference means. For example, very accurate frequency standards. These sound signals you hear are being broadcast from Washington and are being used for comparison purposes. And this is where we calibrate the equipment for all our laboratories.
The Electronics Laboratory, an integrated support facility for the study of long-range ground-to-air communication, nuclear burst reception, and related subjects. A facility geared to develop critical electronic components in support of complete space vehicle systems, a means of tying an invisible but unbreakable chain to our 3 men in space. Construction of spacecraft is not restricted by lack of power or aerodynamic limitations, but by structural integrity. The ability of materials to retain strength and not burn, melt, or evaporate under the fantastic speeds, stress, and temperature changes encountered in space flight. Conducting extensive exploratory research on this problem is the Materials Development Laboratory. It is under the supervision of Mr. Harry Pearl, who has had years of experience, 27 of them, in scientific and technological fields, rocketry, radar, and materials development.
The Materials Laboratory is working on 2 fronts to give our project designers the best possible materials for structures, components, and equipment. On one hand, the laboratory is engaged in evaluating existing materials, high-temperature metals, plastics, and ceramics. Simultaneously, it is developing new and exotic materials, such as intermetallic compounds, alloys, and blends of ceramics and metals. And here again is Bob Rickles.
In the spectrographic room are spectrograph, recording microphotometer, and X-ray diffraction equipment. And this is a recording spectrophotometer. The work here requires the use of specialized furnaces, such as a 60-kilowatt electron beam furnace. A moly disilicide furnace, a graphite tube furnace, vacuum arc, and related equipment. This area is our mechanical testing section. It includes a tensile tester which can test under actual space conditions. Extensive exploratory work in both metals and non-metallics can be undertaken here.
Microscopy with equipment that ranges all the way from an electron microscope with a magnification to 150,000 times to a high-temperature X-ray camera.
Did you say 150,000 times?
Yes. And I could go on, showing you more equipment. But I think you get the general idea. It was our aim to design into this testing facility every working tool the scientists could conceivably need for the space program. I think, and in fact I know, we have achieved this purpose.
And that's the picture in the Materials Development Laboratory, whose goal is to make Apollo impregnable to the elements, impervious to any and all atmospheric conditions, sheltered from the cold, protected from the heat, safe from the hazards of its forthcoming journey.
There is no atmosphere in space, no protective envelope, no shield against cosmic radiation, no haven from meteorites. These are the things which we must provide for the astronauts.
And in charge of this next laboratory is William Helvey. He is a doctor of medicine, graduate of the U.S. Naval School of Aviation Medicine, flight surgeon, and pilot.
This is the Space Environment and Life Sciences Laboratory. In the heart of our lab is a specially designed space simulator, which is 30 feet long and 13 foot in diameter internally. It's the largest in the United States, capable of simulating an altitude of 150 miles or 750,000 feet, and of safe manned entry.
Dr. Helvey, why is it so big?
Here's why. So we can put the entire vehicle inside, 3 men in all. The significant point to remember is that with the increase in performance of present-day high-performance vehicles, both aircraft and spacecraft, there's a corresponding increase in hazards to both men and materials. There's just concern over how men and materials will withstand the new environment, how they will withstand aerodynamic heating, radiation, temperature changes, ranging from a minus 100 to a plus 275 degrees Fahrenheit. This is the reason we exist, to simulate this environment and to test the systems under the situation.
May we go inside?
Yes. As you can see, it is divided into 2 locks. We are in the smaller of the 2, the entry or personnel lock. This lock will usually be maintained at an altitude equivalent of about 30,000 feet. Here is the larger lock. And it is capable of going to the ultimate altitude for which the chamber was designed, 150 miles. We are now lowering the main door. The maximum altitude will be achieved by the use of 3 mechanical pumps and an electronic vac ion pump. The largest vac ion pump, incidentally, built to date. And here's the control panel. When everything is functioning properly, the green lights go on and stay on. We will also have a 28,000-pound vibrator which can be coupled with the chamber to combine vibration and vacuum testing. And present plans include a solar simulator which will simulate sunlight in its intensity and wavelength. And there's a great deal more. In addition to this, the major tool of our laboratory. We have additional labs within this lab. These include plant physiology, and here you see we're trying to determine the necessary conditions to grow plants in a lunar greenhouse. Others include biophysics, instrumentation, microbiology, biochemistry, psychology, and physiology. We will want to know the blood pressure, heart rate, temperature, and other reactions to space flight of our Apollo crew. This, no doubt, will be influenced by what they feel and see. And speaking of seeing, you may have wondered about the size of the windows on our Apollo vehicle. These large picture windows will not be on the actual vehicle. These are made large so we can see in. Of course, they don't have to be that large to see out. This vehicle is presently being used for studies to integrate the man and his equipment.
What about your schedule, Doctor? Your timetable? Where do you go from here?
Well, our current program calls for simulating space conditions for tests of missiles, satellites, and their components, tests of spacesuits and space capsules, the action of lubricants in the ionospheric environment, and the reactions of materials to X-rays, ultraviolet rays, etc. And, of course, we're studying the present Mercury program with great interest. Lessons we hope to learn from Mercury will give us many answers that we're already guessing at.
That should keep you busy for some time to come. What about the target date? When do you expect you'll be ready?
I hope we'll have an orbital station by 1965, and 2 years from then, Apollo, up and around without landing, a 2-week trip, by the way. I anticipate unmanned soft landings on the moon by 1966, if not before.
What about man on the moon?
But possibly sooner. Perhaps the work we do here will make it possible.
When the time comes, Dr. Helvey, would you go up if you could?
Yes, I could. If I could, I would. I used to fly in jets, and the philosophy of a flight surgeon is that he does what the pilot does. If we assume the risk to be equivalent to that of a test pilot, I would be interested.
Thank you, Dr. Helvey.
You're welcome.
And that's the story on the Space Environment and Life Sciences Laboratory and the beginning of the Apollo story. We have chosen to use it today as an illustration of part of Republic's capability, a capability which springs from knowledge. Our heritage of aerospace knowledge is nowhere more evident than in this library, which contains over 70,000 scientific volumes. But even in so comprehensive a collection, there is little of our recent projects. These include a plasma engine laboratory, which is developing now a revolutionary interplanetary space engine, an engine successfully tested in its pre-production model. Such exciting developments are a direct result of the policy at Republic, where we do not separate spacemen from aircraft men. We are one in our effort, working, planning, and accomplishing the objectives of our country. In this, however, we need not work alone. We do not feel that it is necessary to design and execute every phase of the projects in which we work, for it is our conviction that to preserve the safety and dignity of the United States, men must work together to master travel through the atmosphere and beyond. With such mastery, we may one day control our own evolution and prevent our own extinction. And in this year of 1961, fulfillment is at hand. With confidence in our ability to realize that fulfillment, we are reaching for tomorrow.